Hey everybody, welcome back to Paleo. So we've covered paleoecology, we're in biogeography, we're going to finish that up today, and then we're going to get in a little bit into biostratigraphy the end of this week. Remember Friday we have off because of Good Friday, and then we're going to finish up with biostrat next week, and we'll have a happy fun time test. So let's talk about that for a second. Again, think of these as like a lifeline and not a shortcut. And talk to your advisor before you do anything. Okay, let us get into today's topic, but before we do that, let's review a bit. So areas at the equator get a lot of rainfall. So most of the tropical rainforests on Earth are at or near the equator due to what kind of winds and what kind of pressure. So I'll give you a second to think about that. Are the winds converging or diverging? And is it low pressure or high pressure? What's happening to the air in low pressure? What's happening to the air in high pressure? What is it that leads to rainfall? So 3, 2, 1. And the answer is converging low pressure. So at the equator, the winds are blowing towards each other, they hit, and they rise. Rising air cools, causes water to condense into clouds, and you get lousy, low pressure weather. It's debatable whether the rainforests are lousy weather, but just a good way to remember it. So low pressure, lifting air, lousy weather, rain. Which of these islands would probably host the most diverse fauna? So what were the two big factors that controlled the diversity on an island? So try to think back. Remember that experiment where they fumigated the island and watched what happened when species started to come back? What were the big factors and how quickly that happened? So there's 4 islands. If you can't see the map here, Madagascar, Seychelles, I don't know how to say that, Comoros, and Mauritius. So the one with the most diverse fauna is going to be Madagascar. So the 2 factors that control diversity is the size and the proximity to the mainland. Madagascar is both the largest, and this might be a little bit closer here, but Madagascar is also very close. So that combination of being very large and relatively close is what leads to the diverse fauna on Madagascar. And we're going to talk a little bit more about Madagascar later on in the lecture. So with that said, let's get into it. So the 2 main subdivisions of biogeography, this slide is the same slide from last time. Last lecture, we talked about this aspect of it. So last time we looked at the present day distribution of organisms, what controls organisms distribution in the present day. So we saw that patterns in temperature, patterns in precipitation or humidity are the dominant factors. And a lot of that was kind of latitude based, but there were also some kind of like local geographic things like rain shadows and ocean currents, cold ocean currents specifically. So that's today, that's modern. We can go look at that today. And the next aspect is historical biogeography, which is basically biogeography through time and examining ancient organisms, ancient arrangements of the continent, ancient climates, and seeing how that affects the distribution of organisms and basically how they got where they are and why they are where they are and why they stay where they are and maybe why they leave. So with that in mind, this is basically reconstructing ancient worlds. So one of the most famous examples of this is Alfred Wegener's continental drift theory. So in the early 1900s, 19-teens, he suggested that the continents drifted around, and he was sort of laughed at by most people, mostly because his mechanism was just that the continents kind of plowed through the ocean crust. So he got the mechanism wrong, but he got the idea right. The continents do move. So that helped put together this story where there's these fossils of Mesosaur is yellow. Mesosaur you see there is a freshwater reptile. So it looks like it can swim across water, and it can, but it's freshwater. So how did we get this freshwater reptile on both South America and Africa? They're separated by the whole ocean. These things could not navigate the open Atlantic saltwater. And then also occurrences of Glossopteris. So Glossopteris is the green here. Glossopteris is a fern. So how do you get a fern on these various different continents? So like maybe with a tree, you could think that, okay, well, the seeds blue or the pollen blue over there. Ferns don't do that. Maybe it was like a log that floated or something. Like, how does that work with a fern? So if you put the continents back together, those seemingly random, inexplicable patches of fossils now make consistent, coherent patterns. This was the range of Glossopteris. Glossopteris didn't need to float. It didn't need to spread its seeds far. It was a continuous patch of land at the time that Glossopteris existed. Same thing with Mesosaurus. Mesosaurus was able to exist in this region, in the rivers in that area. It didn't need to swim across the Atlantic because the Atlantic wasn't there yet. So using this historical paleogeography approach, we're able to kind of like build these pictures and reconstruct what things were like. And remember from last time that one of the most important factors of where critters live is what the conditions are there, particularly temperature and precipitation. So we also have to reconstruct the ancient climate. So how do we reconstruct ancient weather patterns? We're getting pretty good at reconstructing ancient depositional environments. So like in said strat class, and to a lesser extent historical, and even a little bit in this class, we've talked about how to read the rock record and kind of think about what the depositional environment might have been like. But there's no real direct measures in the rocks, the rock structure, the rock texture of what the weather was like, really. But marine organisms incorporate isotopes of carbon and oxygen into their shells, which are made out of calcium carbonate, CaCO3. And that makes it into the limestone and makes it into the sediments that they occupy. And these isotope ratios vary with time, and they also vary with climate. So if we look at the chemical signatures of these isotopes in ancient preserved shells or ancient sediments that have these carbon and oxygen isotopes, we're able to kind of reconstruct what the weather might have been like at that time and the place. So how does that work? Well, let's look at 018 first. So you might see the nomenclature like this with this little goofy letter here. That's the Greek sigma. So sigma 18O through time. So with oxygen, 018, 18 is the atomic mass, 018 is 2 neutrons heavier than 016. So 018 is a bigger molecule. It's a heavier molecule. So when you're evaporating seawater, the heavier molecule is harder to evaporate. And so 016, the lighter molecule, preferentially gets into clouds, and clouds make rain. So it's preferentially in precipitation. Freshwater rivers, glacial ice, those are fed by precipitation. So they are also favoring the lighter 016, and they're quote unquote depleted in 018. So the oceans have a higher 018 content than the stuff that comes from the evaporation into the atmosphere of the ocean water. It's called fractionation. A small fraction of that 018 makes it up in. And it's not a huge percentage, but it's relevant and it's measurable. So if we, with that in mind, if we look at changing 018 values, and here is a 018 curve kind of a smooth long-term average, and then more of like a short-term spikier average. What we can see is that on here, there's 018, delta 018, change in 018 or deviation in 018. Going down this way is positive, so more 018, and going up this way is negative, that's negative 018. So higher oceanic, and remember that's where the critters are living and building their shells and where most of the rocks are, higher oceanic 018 values means that there's colder glacial times because more of that lighter 016 is being locked up in glacial ice. So if more of the 016 is locked up on ice on land, there's relatively more of the 018, the heavier stuff, left behind in the water. And so we can use the 018 to kind of reconstruct this, and it fits very well with the geologic rock record for when there were glaciations and not. So there's another like kind of independent calibration on that. But this is all the various processes. You can see all the different fractionations that happen along the way. So very useful. We're able to reconstruct climate from 018. We're also able to reconstruct climate from C13. So similar processes, again, C13 has one more neutron than C12. It's a heavier, larger molecule. So again, when it's exchanging ocean to the atmosphere, the heavier carbon-13 tends to get left behind, and the lighter carbon-12 goes up in the atmosphere. When trees are photosynthesizing, when they're transpiring, when they're making energy, building plant tissue, the carbon-13 tends to, again, be kind of left behind in the air. The plants preferentially use the lighter, easier, smaller carbon-12. So kind of the opposite of the 018, when we have lower oceanic 13 values, that indicates colder periods because there's less of the carbon-12 locked up in vegetation and in carbonates. So during very cold glacial periods, there's a lot less biomass, there's a lot less vegetation, there's less trees, there's less grasslands, there's more desert, more ice covering the land, and so there's less carbon-12 being locked up in plant tissue. And also remember that most carbonates, not all, but most carbonates are warm water, tropical carbonates. And if we have a colder glacial period, there's not as much of that going on. So again, this is, looking at dates here in millions of years. This is going back to the very latest Proterozoic into the Precambrian. And what we see is that, again, we track this delta carbon-13, down is minus and up is positive. When we have lower values of carbon-13 in the ocean, it means it's colder. And what we see is that during these low carbon excursions, we have evidence of these massive glaciations. In this case, these are the snowball Earth events. So when Earth almost froze completely over, and this one's probably responsible for the great unconformity that we see pretty much everywhere on the Earth. But again, just looking at these ratios, we're able to reconstruct past climate. So it's difficult, and it's really hard to say for sure exactly what the temperature was, but relatively warmer or colder, or saying we're in like ice house conditions to make glaciers, or whether we're in like hot house or greenhouse conditions where we would be warmer, that's relatively easy to see with the directionality of these isotopes. All right, so that's the controllers on that. So let's talk about how animals get places. So there's this concept of biogeographic dispersal. So it's basically explaining organism distribution. Originally, there was this idea that everything kind of had a center of origin and everything radiated outward from that center of origin over time. Again, that's kind of like going back to like the Noah's Ark idea, where there was like the central location and all animals kind of migrated out from there. And we definitely see examples of dispersal. So one of the more famous examples is this one here. This is the out of Africa route that our human ancestors took. And this map is getting redrawn like basically every week now. But the gist of it stands strong. So the most ancient hominid fossils occur in Africa. There's very little disagreement about that Africa is like the cradle of humanity where we originated. And then the first place that we start seeing is into the Arabian Peninsula. They dispersed to the closest places first. They did not go into North Africa. So let's think about that for a while. North Africa, they arrived much later. I wonder why that is. What is right here in Africa? Oh yeah, the largest desert on Earth, the Sahara Desert. So good habitat acts as corridors, acts as pathways. So organisms can take this, like these paths that are well connected in habitat that's favorable to them. So like, for example, walking from Africa into the Arabian Peninsula, conditions don't really change all that much. The habitat, if you liked it over here, you're probably gonna like it fine over there. As you get further and further away, it's a little bit more and more different, and so you have to adapt along the way. But you can find these corridors that you can migrate through. Geographic barriers are things like mountains or oceans, or in this case, deserts that block those corridors, block those dispersal patterns. And so then we kind of move here, and then we see another kind of bifurcation where some things went this way, some things went kind of this way, nothing went straight north. So why is that? Oh yeah, the Himalayan mountains, the largest mountains on Earth, formed a big barrier, and so some people went around this way, some people kind of went around this way, nobody went straight over the top. And then one of the last barriers here is getting into like the Southeast Asian islands. Again, here oceans are the barrier, and there's a lot of kind of sketchy dates on when people arrived on various islands, and that's always being reworked. But this is just a general story here, subject to change, obviously, changing rapidly, very rapidly. But this is kind of the general picture, and it just shows a dispersal from a central point relatively quickly in geologic time, and these corridors being bounded by these barriers. So one mechanism that we see is dispersal through what's called filter bridges. So in a lot of cases, it's not as simple as just like walking across the land to as far as you can possibly walk before you hit a barrier. Some corridors are better than others, and some corridors are not like just open two-way freeways. Some cases, only certain organisms use the path. So like this cartoon here from Asia to South America, it says bears only. So this bridge is perfectly fine, but for some reason only bears used it. Or it's only one way. So going from Australia to Antarctica to South America, and very rarely, if ever, the other direction. Or transporting completely unbalanced faunas. So remember, there's this idea of, you know, the trophic pyramid. There's really no restrictions on which parts of the pyramid show up. So in a lot of cases, you have these like giant animals showing up preferentially, or maybe you have the smaller critters showing up preferentially. It doesn't have to be like a balanced, harmonious ecosystem that moves along. It can be biased towards certain things. So one of the famous examples of this is the Bering Land Strait. We'll talk a little bit about more in detail. But there's kind of this funny cartoon here. This is the filter. So camels and horses, they went this way. For some reason, peccaries, pronghorns, raccoons, and ground sloths didn't. So like you think about like a pronghorn and a horse, or a pronghorn and a camel, four-legged, largish herbivores. relatively similar lifestyles, sharing similar habitats. Why did horses and camels decide to cross the bridge and pronghorns didn't? Who knows? But it's interesting. There's a bias here. Same thing here, like mammoths, bison, bears, deer, they went this way. So we kind of think about like American bison as one of our like national symbols. Bison didn't originate in North America. They originated in Asia, and they came over across the Bering Land Strait and started populating the areas in North America. Mammoths also made that transition in some other larger animals, but a lot of the animals that we associate with North American deciduous forests, they're not native to North America. They came over on the land bridge, but things like rhinoceroses, hyenas, gazelles, it didn't. And then one interesting one is pigs. Pigs are everywhere in North America now, but they didn't actually get here over the land bridge. They only came later when European settlers brought them. They never made the trip. So kind of interesting. So again, like this idea of a bridge, but it's not a universal freeway. It filters in some way. And why it might be, I don't know. Maybe that'd be a good topic for discussing, for example, in a board of discussion, a discussion board, yes. So that might be a good thing to talk about in there. Remember, you can start your own threads. Another way that things get around is it's called sweepstakes dispersal. So sweepstakes is kind of like an old word for like lottery. So some distributions can't be explained by walking at all. So like some human dispersal, they couldn't walk there. They had to have gotten there some other way. So they swam there, they boated there, whatever. But to cross a major barrier like open ocean, it takes some kind of extraordinary event. One of the most extraordinary events you can have is winning the lottery, so that's what they call it, sweepstakes. The animal that actually makes that trip fully across the barrier and survives to the other side and establishes a new population, that's an extraordinary event. It's incredibly lucky, incredibly fortuitous. Some ways it can happen is like long distance swimming. So like we think of elephants as big and lumbery, but they're actually quite good swimmers. They've been seen traversing pretty large expanses of open ocean to get to islands. So like maybe mammoths could do that too. Very similar animals. So it can be kind of surprising how far an animal can go through an allegedly impassable barrier when it's kind of forced to. Like if an elephant gets washed out to sea somehow, like a big flood or a tsunami or something like that, it's got two alternatives. It's going to die, or it's going to swim and it's going to make it to dry land. Remember that history doesn't record the losers. So a lot of these things that would have become the sweepstakes dispersals, they did not make it. But the ones that do are able to establish new populations. So it's incredibly unlikely. It takes a lot of fortuitous events to happen, but it definitely happens. And one of the better known examples of this is the Japanese tsunami, the one that knocked out the Fukushima nuclear reactor. There's actually this example of this dock that traveled all the way across the entire Pacific and docked on an Oregon shore, and it still had essentially its entire fauna in place. So these like Japanese sedentary, sessile, filter feeding biota that were stuck on the dock, and even some other things that were on the dock, they made it all the way across the ocean by hitching a ride on a raft. They rafted their way across. And this is probably another way that islands can get seeded with things that kind of look like, how did that get there? What happened here? So another thing that happens is like mangrove forests, coastal mangrove forests. We've done a lot to disrupt coastal mangrove forests around the world, but they are a very important coastal buffer against hurricanes. And when hurricanes roll in, they can actually like tear off large pieces of the mangrove forest, and it just kind of floats out to sea as a floating like island basically. And those floating islands contain life. So there are documented evidence of like tiny mammals, like rodents and things like that being hosted on these small floating islands. Again, it's very likely that at some point the island's going to capsize or break up or be swamped and you're not going to make it. But again, we're talking about the ones that won the lotto here. Some do, some win the lottery and they make it through. Another dispersal mechanism is Noah's Ark dispersal. So we talked about just dispersing by walking, then we talked about dispersal by swimming or rafting or some other incredibly unlikely process. Another way that you can do it is you don't even have to walk at all. You can just chill out at home in your ecosystem and you let the land do the walking. So like the best example of this is probably India. 71 million years ago, India was way out in the ocean. There's no chance at this point of, well, very little chance of any Indian fauna making it to Eurasia when India's this far away. As plate tectonics moved, you see the rate here, 5 to 15 centimeters per year, pretty slow, about the rate your fingernails grow. But given 71 million years, it adds up. So all the fauna on the Indian subcontinent are kind of going along for the ride. It's like this massive boat. It's like an ark. The animals are way more than 2 by 2. It's all of the whole population going at the same time, going for a ride. As it gets closer and closer and closer, that sweepstakes migration probably becomes a little more likely. And then when it docks, all of a sudden now that regular dispersal via connected corridors becomes a possibility. So all the flora and fauna just kind of go along for the ride. And when it docks, they can get off. So it's very much like Noah's Ark. So Noah's Ark allegedly landed at Mount Ararat, and then all the animals got off and spread off to the various corners of the world. When India docked, the Indian fauna spread off into various corners of the world. Some got outcompeted. Some outcompeted the ones that were in their other niches there. But it was kind of like this new mixing of these fauna that hadn't been in this before because they kind of hitched a ride. And then the last mechanism is Viking ship funeral, Viking funeral ship dispersal. And it's pretty similar to Noah's Ark dispersal in that the organisms don't walk, but it's a little different in that they don't even need to be alive. So as India was going along for that ride and smashing up into Asia, all of the rocks of India went too, and all those rocks contained all the fossils. And so all those ancient organisms that were preserved on that continent went along for the ride. And obviously, like India's tectonic motion history is very different from Eurasia's. And so there's this, if you look at that seam in there, there's this sudden change in the fossils where fossils on the Eurasian continent have a very different history, very different climate, very different a lot of things to looking at the Indian fauna. The key distinction here is that when the ship, quote unquote, docks, obviously the fossils don't get off. So unlike the living animals that can actually kind of disperse into the new environment and start competing with the endemic fauna, the fossils stay where they are. But a good example of this is if you look at the Western United States, our quote unquote North American craton. Remember, cratons are made up of a lot of different exotic terrains that weren't always part of our continent. And so there's all these pieces that have been plastered on over time, various different times, and all of these pieces moved from different parts of the world at different times, from different climates, and they brought their fossil record with them and kind of glued it on to North America. If you look at the eastern coast, it's the same thing. We see Taconic Ark, the Acadian Ark, the Allegheny and Rajni plasters on some pieces. So like parts of Scotland are actually originally North America. Parts of New England and Eastern Canada are originally parts of Europe. And so when it split, it didn't split evenly. And so those different pieces that are now very far apart look like they were originally connected because they Viking shipped apart. And then the last one is this idea of escalator counterflow. So there's this weird idea that organisms can actually be older than the land that they currently occupy without having really ever gone anywhere. So a good example of this is Iceland. So Iceland is an island on a hot spot above a mid-ocean ridge. And it's probably been there for 60-ish million years, maybe longer. It's been there for a while. But the rocks themselves are only up to about 10, 12, maybe 13 million years old. But a lot of the organisms have been on that island the whole time. So how does that work? Well, as Iceland is moving under their feet, new Iceland is being created, old Iceland sinks away. The animals stay on the high and dry parts. So it's like the Iceland's moving down the escalator as they kind of run to stand still. Another example is Hawaii is on that spot right now. It's volcanic and dry. The other islands are actively, but basically as islands are saying, the fauna kind of abandons an island off to the next island. And so fauna that existed on the island jump on the island. And so they're older than that new one. So it seems impossible. Some organisms are older than the land that they're on because the land is recycled land. They're running to stand still. They're counterflowing up the escalator. So let's look at some examples. So Bering Land Bridge is one of the famous ones. So as sea levels dropped during glaciation, so again, water locked up on land, sea levels drop, it exposes this dry connection between Asia and North America. And then the glaciers start melting and that connection goes away. So here's 20,000 years ago at the last gasps of the glaciation, the land bridge is pretty well established. The ice starts melting and it starts going backwards. It starts more resembling the modern coastline. But again, this Bering Land Bridge, it didn't seem to be like an open 2-lane highway. It was a filter bridge, so not all organisms crossed, and it was dominantly to North America. So most of the travel was to North America from Asia. So like if you look at what stayed at home in Asia, pigs, rhinoceros, gazelle, these are all the things that immigrated to North America, a pretty large list. These are all the things that immigrated from North America to Asia. And again, you see like, not a very large list there, horses and camels really. And a few decided to stay home. So like our raccoons decided to stay here, so that's nice. But again, not all organisms crossed. It wasn't perfectly two-way, there was asymmetry there. So that's a good example of a filter bridge. A good example of the sweepstakes migration is the mammals of Madagascar. So you probably saw the movie focusing on, I think the lemurs are the main point, but basically Madagascar is this island off the coast of Africa, but it was connected to Africa. In fact, it was connected to South America, Africa, India, Antarctica, and Australia. And then it rifted off of Africa as part of the Indian subcontinent. And then they separated about 88 million years ago. And then they've been kind of drifting separately ever since. India drifts all the way to the Himalayan orogeny point. Madagascar stayed mostly where it is. I'm not actually sure if it's moving or not. If it is, it's very slowly. But what you see here is that as of, say, 80, well, let's say 135 million years ago, there's a disconnect here. There's a barrier to dispersal. And then even in the present day, there's still a barrier to dispersal. But what we see is that there's these certain animals, most notably the lemurs. Lemurs start appearing on Madagascar about 60 million years ago. Well, that's weird, because 60 million years ago, the Mozambique Channel's already there. There's already this barrier. They're not connected. So the lemurs couldn't have walked over. How did they get there? Well, what we see is that most of the animals that made the trip are smaller. So there's like a bias here towards smaller sized mammals. And so it's suggesting that it wasn't the land bridge or all these big mammals would have come over. So what could it be? Well, the illustration kind of gives it away. The idea is that they rafted over. So like the lemurs caught a ride on some piece of floating debris, probably not on purpose. It's probably a very harrowing experience to be catastrophically washed out to sea and clinging to some sort of organic life raft that was obviously not designed with purpose for floating. Most of them probably didn't make it, but some of them did. And they established a population on Madagascar that's been thriving ever since. And so there's an extraordinary diversity of lemurs on Madagascar because they've been isolated from the African population of lemurs for 60 million years. And again, it's a relatively large island, relatively close to the mainland. So this enables emigration, this sweepstakes dispersal every once in a while. But things like elephants, lions, they didn't make it. It looks like hippopotamuses actually did. Now, a hippopotamus isn't gonna be able to raft over on something, but they probably actually were able to swim this distance. Some people have done some modeling that this rafting wouldn't work now because the Mozambique Channel has incredibly strong currents, but they reconfigured the basin to paleo conditions and found out that up to about 20 million years ago, it was still probably raftable. And that's what we kind of see in the fossil record, is that this rafting emigration, the sweepstakes dispersal, sort of shuts off at the time where they sort of predicted it would, when the currents sort of initiate. So kind of neat. Another good example of this dispersal is the marsupial migration. So when we think marsupials, we think Australia, but that's not always the case. People thought that this large diversity of marsupials in Australia kind of meant that, well, they started in Australia and they dispersed outward from there. But what we see is that that's not true. Marsupials originally thought to be originated in North America, but then it's actually been found out somewhat recently that they're more from South America. And to get to Australia, they moved through South America, through Antarctica, and then they ended up in Australia. So as these things were kind of rifting apart from Pangaea, the marsupials kind of followed the floating rafts, and they ended up isolated on their own little raft in Australia. But that's not where they started. They walked there when it was still connected, and they've been floating on it ever since. So like, obviously Antarctica, I don't think has any existing marsupials. South America has limited. Central America has a few, and North America, like actual United States and Canada, only has one, our good friend the opossum here. So sort of interesting. They didn't walk to Australia. They didn't float to Australia. They hitched a ride on the floating continents, and they walked onto them, and then they kind of left port, and they went along for the ride, and they've been going for the ride ever since Australia has been disconnected. And Australia is obviously a very large island, and they evolved to fill all the niches that placental mammals fill on the other continents. And then the last example here is, it's called the Neotropical Interchange, or sometimes called the Great American Biotic Interchange, or the GABI. And it's basically fauna coming across the Panama Isthmus. So it's, again, kind of weird. It's an example, a really good example of a filter bridge. So very few animals migrated from South America to North America. If we look at these silhouettes here, these are the ones that came from North America, or sorry, came from South America to North America. And these silhouettes here are the ones that came from North America to South America. So if we look at all these silhouettes here, giant sloth, glyptodont, some kind of large flightless bird, those are extinct. Capybaras are still alive, but they're in South America, or Central America, also South America, but they don't make it up into North America. The only thing we've got here is possum. But going the other way, all these critters went the other way: rabbit, squirrel, skunk, fox, pigs. So the North America fauna really kind of won this negotiation. So they walked across the bridge and they started out competing. They started replacing South American fauna, and it didn't work the other way around. Very few South American fauna went up into North America and outcompeted the North American fauna. So why would that be? What advantages did North American fauna have? So one of the conversations posted in the discussion board is, what is inherent about like the North American fauna that would make them better able to compete? So think about what it would be like migrating from north to south across the Panama Canal, what would be happening, versus going from south to north, what would be happening. And then also think about the relative sizes. So remember, diversity is a big key. Size of the landmass is a big key for diversity. And then also remember, there was also a land bridge up in the northwest, right? The Bering Land Bridge. So how does that help the North American fauna compete? So think about those, post up your thoughts in the discussion board, and I'll see what that is. And then the last slide is this idea of, so this whole kind of revelation, this whole link between like biogeography and then extending it to paleogeography with the invention of plate tectonics, it kind of spawned this whole like way of thinking about things, which is called Vicariance Biogeography. And so it was this kind of idea, and it started off relatively radical, and it's sort of tapered a little bit since then. But it's this idea that the existing ranges when it originates, everything goes to the maximum possible extent almost instantly. And the range that we see now is a result of kind of breaking that original extent down. So it's kind of almost the opposite of dispersal, where you start small and you go to the big picture. It's that it starts with the big picture and then things kind of like wear away. So their name for it comes from this idea of, so vicars. So like if you hear the expression like living vicariously, vicar is like a replacement, or like in the church, a vicar is like the representative of Christ. So vicar is a representative. Vicars represent existing fragments of the formerly much larger range. So for example, these dinos here used to be over this whole continental landmass, but they've been split apart by time and space, never to be reunited again. And then what this led to is that there was kind of this, we talked about it earlier, the like Darwinian evolution versus cladistics, like taxonomy versus cladistics. This actually started making these branches of almost like cladograms, and what you see here is that these are continents. So like Pangaea was all the continents, then Pangaea broke off into Laurasia and Gondwana land, and then Africa and India broke off from there, and then Africa and India separated from each other, along with Madagascar, going this way. Then we start branching off into all the other continents. But basically we made these like branching trees of the continents, and then you start comparing branching trees with the animals, and if you plot them up together and there's a good match, it probably argues that this idea that dispersal happens through some of these fragmentation means probably starts to hold up a little bit. So that's all the material for today. Just make sure that you're hitting up that discussion board. Again, it's a short week. There's only the Monday class and the Wednesday class. So just make sure you get in 2 posts. Remember, you don't have to wait for me to start a thread. You can start a thread if there's something you thought was interesting, if there's something that you thought was confusing. Office hours have been mighty lonely, so remember that if you have a question, feel free to drop in, or just click the link on the email that I sent out, the Zoom link, and you can also contact me via email. You can contact me via phone. Don't feel like you are left on your own. And that's all I got for today. There's the disclaimer, yada, 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 yada. So I hope everyone has a good day. Hope everyone enjoyed their weekend. And I shall see you on Wednesday.